screen, right? Okay. So, in ME430, one of the things that I want to clarify here, how many of you had the ME430 and ME530 in this semester with me? I mean, the both classes. Anyone here? Okay. One of the funniest things that the department does is offering two courses at the same semester. They are very, very similar. Okay. I have no idea why they are doing that. So if you see very similarity between them until some point, this is based on the syllabus. Okay. I mean that they are the same course almost except the end sections. I'm trying to teach differently, but um, if you want to drop one of them, that's fine. See what I'm saying? So, uh, in other universities, they are offering these courses in different semesters. Because ME430 is elective, right? As I know. Yes? Yeah, okay. Also, ME530 is elective. I don't know why they are offering it the same semester. I told them, but nobody listening to me. Okay, so I'm telling you that the modeling of physical system and modeling of physical systems and control automatic control syllabus, they have say 70% overlap. Okay, so don't waste your time on both of them. So how I'm gonna teach the course as the students that they had course with me, I'm very I have emphasized on the implementing the theory that I'm teaching in the class and the math, because my classes are very heavily math based. Okay, into MATLAB and Simulink, because I want to make you expert of the MATLAB and Simulink when you pass this course. Because if you go to industry after passing this course or after getting your bachelor's degree, and if you're not expert of the MATLAB, you're not engineer. You are whatever, what you are not engineer. So you're gonna see everything that I'm teaching in every class. Eventually, I'm gonna develop its code and in Simulink file. Okay, and I'm gonna share those files with you for your exam, for after graduation when you are working or whatever. So, modeling of physical system. So, as its name implies, we are trying to develop a linear model of physical system. This physical system. I'm saying PS, physical systems. Linear model. When I say linear, I mean that linear differential equation. Linear differential equation. Those of you that you had vibration course last semester, you know what I mean, right? Linear differential equation. Because in undergraduate level, you only deal with the linear differential equation. If you, by applying Newton's second law that I'm going to teach step by step at the moment equation, or I don't know, fluidic equation or electrical equation that I'm going to cover in this class, or electromechanical. So in this class, we're going to derive mechanical differential equation, fluid differential equation, electrical differential equation, electromechanical differential equation, and heat transfer differential equation, heat transfer. And what are we gonna do? We're gonna derive the differential equation maybe in the nonlinear format, maybe, and then we're gonna transfer to linear format. First nonlinear, maybe, nonlinear. Then, how we do that, guys? Those of you who had vibration with me, then transfer to linear format. How are we gonna do that? Nonlinear to linear? Any idea? Through equilibrium point. Remember that I was teaching in the vibration class, equilibrium point. So I'm gonna cover here. So, new slides. So, let's go to very famous that always I'm teaching in all dynamics vibration control robotic classes to give you first I'm gonna give you some ideas about how to derive nonlinear differential equation, and then how to make it linear around equilibrium point, what is equilibrium point, and what's the solutions, what the stability, instability, and then we go from there. I'm gonna define you the Laplace transform, and then we continue the course. Okay? So the most famous problem in all universities around the world for undergraduate and graduate courses, what's the name of this, guys? I want that you tell me. What? Yes. You have seen this in my vibration class, right? Good. Theta L M. And because I'm teaching from my mind, I never have a note, okay? Because I don't believe notes. If I have the knowledge, I can teach from my mind. In some places, I may have some stupid mistakes, so follow me, okay? Okay, this is pendulum. This is a model of your hand. So in this class, you're gonna learn how to model different systems based on differential equations. The name of the course is that, right? Even in the control class, first we have to do some modeling, and then we go to control theories, okay? Model of your hand. This is your shoulder joint. And assuming that the mass of your hand is lumped at the end, M, and the mass of this link of your hand is massless compared to the this M, okay? So, and I'm assuming that there is no friction, rotational friction at the joint. So mu at A is 0. There's no friction here. Because if it's friction, I taught in the vibration class, you're going to have a very different, very nonlinear differential equation. So we don't want to do that. So based on the moment equation, because as you learn the dynamics course at SDSU, if not in the vibration class of mine, that for rotational motions, we're gonna use moment equation. Sum of the moments around point A, a fixed point, is mass moment of inertia of the mass around point A in angular acceleration, theta double dot. This is moment equation. I hope that all of you know about this, right? Yes, moment equation. This is rotational version of Newton's second law. Sum of the forces is called the MA. Okay? So this is mass moment of inertia. Mass moment of inertia, angular acceleration, and this is the sum of the moments. So we are in mechanical system first. Okay, mechanical system. So as you know, based on the dynamics, we're gonna cut from the system from here for free body diagram to derive the differential equation. then I'm gonna plot what? Forces acting on the system. So it's gonna be mg. But here we don't need this because only system acting on the system, they are the mg, mass of the weight of the mass, and the reaction forces from, oh my god, what happened? Point A. And reaction forces from here, say Fx at the support. You know from statics, that's right, and dynamics. And the Fy. Right. So then you have to find this, for the moments, these distances from the trigonometry from kindergarten. Here is L cosine theta, and here is L sine theta. Clear, guys? Yes? So some of the forces around point A. So does Fx and Fy generate any moments around point A? Do they generate any moment? No. Why? I told you. Exactly. They are passing through the point A. So only is mg. We know that the moment is force in normal distance. Normal distance to the point A, normal distance, it is 90 degrees, is Lg sine theta. Positive or negative? I taught you. But I'm going to teach again here for those that you had no vibration. So positive or negative? Because moments always has sign. Always. Like force. Force has sign. Right? It's positive or negative, guys? It's negative. You're gonna tell me based on clockwise, counterclockwise, but I hate that, you know that. The simple rule is that we're trying to increase the angle of the hand, but the mg trying to resist the motion. That's right. If you fix, and this is fixed point, so if you apply the m, it's trying to pull back the hand. That's right. Yes, everyone? Yes? Okay, so resisting means negative. So please memorize this. Resist means negative. Helping the motion in any system means positive. Simple like that. Resist means negative. Helping means positive. So mass moment of inertia around point O, because this is particle, so around its own mass center, I taught you a million times, even in dynamics, is 0. So we're going to use the parallel axial theorem. Gonna be, look at here, it's going to be like this. Let me write. I around the own mass center plus m d square theta double dot. Because this is particle, has no dimension. Anything has no dimension, these are basic from dynamics. Its mass moment of inertia around its own mass center is 0. So remaining is m, and if you path two normal axes inside the page from point A and point M, that's right, the normal distance between them is how much? L. So this is gonna be ml square theta double dot. Anyone understand this? Yes? Okay. Who was your professor at the dynamics? Oh, she's my friend. I cannot insult her. So, so okay. You tell me first. What's the difference between rigid body and particle in dynamics course? No, exactly. You are very mistaken. Ah, rigid body has dimension. Particle has no dimension. Okay. Both they have mass. If either of them has no mass, they don't exist even, man. Okay. Why we are solving for that? See what I'm saying? Okay. So, and if you remember from dynamics, mass moment of inertia is being defined as integration of r squared dm. This is from dynamics, ME2 and 2, ME220, right? This is how we define mass moment of inertia. So this is distance. Okay, what's your name? Joey. This is distance, r. Okay, or dimension. So this particle, m, has no dimension. So how much is the I? No, no. This is dimension, r. Okay, this is dimension. Dimension of particle is how much? I told you. Means no. See, again, particle and rigid body, they both have mass. Only difference is that particle has no dimension, rigid body has dimension. So when I'm saying particle has no dimension, means R is how much? No, zero. Has no dimension. See what I'm saying? See what I'm saying? Has no dimension. Okay, so this is zero. So I of that around its own mass inner C, here is C. C is how much? Zero. See what I'm saying? See? Particle, I'm writing here, has no dimension. Rigid body, I'm writing like this, has dimension. Mathematically speaking, when I say has no, means has no dimension, means dimension of this how much? Is zero. When I say has dimension, means is not zero for rigid body. See what I'm saying? Yes? Okay. Now, we are defining from dynamics mass moment of inertia integration of r squared dm. R is dimension. So for particle, r is zero. So I around its own mass energy is zero. See what I'm saying now? Yes? Hello? Can you hear me? See? Clear? Maybe this is not only your problem. Maybe few of you have the same problem. If it's not clear, let me know. I can go back to dynamics. R is zero because it has no dimension. Can I go ahead? Yes? Okay, okay. So now, in the dynamics, we have the parallel axial theorem. The remaining is MD. D is the normal distance between the axis that we are passing through between point C and point A. They are normal to the page, out of the page. So the normal distance between them is L. Okay, L square. So if I rewrite that in the next page, I mean that if I move this to the other side, where is that? New slide. So you're gonna have ml square theta double dot plus mgl sine of theta is 0. This with this goes to the New York. This with one of the square goes to Denver. So if you multiply the both sides by L, so you're gonna have theta double dot plus G over L sine theta is 0. And this is differential equation describing the particle pendulum as a simplified version of a simplified model of your hand or your leg. But this is linear or nonlinear, guys. This is linear differential equation or nonlinear? You tell me. Any idea? Yes, nonlinear. Why? Yes, because of sine theta, because sine is nonlinear by itself. See, this is a nonlinear function, guys. So this differential equation is nonlinear differential equation, NDE. So because in this undergraduate course that we're going to model the system and then transfer to the Laplace domain or frequency domain eventually, we cannot do that because Laplace is only for linear systems that I'm going to teach. Okay. So what we're going to do, we're going to linearize it. We're going to linearize it around equilibrium points of the system. Linearize around equilibrium point of the system. Around equilibrium point of the system. So equilibrium point is a point that the system is at rest if you do not apply any external force or moment or excitation. This is the definition of the equilibrium point because you have to know it's fundamental. Okay, guys? So when I say at rest means what of the system is 0? Suppose that you are at rest. Your car is at rest. What of your car is 0? What of the car is 0? What? No. Just use your eyes. Just use your eyes. You're looking at your car is at rest. And so in your car you have a gauge when you're driving, it's changing, that's right. What is that gauge? You see that? Yes. First velocity and then acceleration is 0. Well, when I say equilibrium point means your system has rest, means it has no velocity, it is stationary, like as a static course, and its acceleration is 0. So if your system has translational motion, means is moving on the straight line, so its x dot and the x double dot is 0, velocity and acceleration. If it's in the rotational motion, so it's theta dot angular velocity and theta double dot angular acceleration is 0. See what I'm saying? Yes? At equilibrium point. Okay, guys? If you're working in the pressure of a tank, P, pressure of a tank, because it has a dynamics, I'm going to teach you, or height of a level of water in a tank, so it's P dot at the equilibrium point, and the P double dot, they are 0. If you're working with the temperature at the equilibrium point, T dot and T double dot, they are 0. If you're working with the kebab, pizza, equilibrium point of that is the kebab dot and kebab double dot is 0. Velocity and acceleration. See what I'm saying? Yes? Yes, guys? Good. Now, we go by this definition of the equilibrium point. Now, all of you that you're sitting and listening to my harsh voice, okay, you are at your equilibrium point because you have no velocity and no acceleration. Simply like that. Okay? So we're going to use and linearize this. New slide. How? Theta double dot plus G over L sine theta is 0. I told you at the equilibrium point, what is 0? I just taught you. Look at the previous page. What is 0? Here we go. So here we go, rotational motion. So what is 0 here? Bingo. For finding equilibrium point, first, if you want to linearize a nonlinear differential equation, you have to linearize around the equilibrium point. So you have to find the equilibrium point first. So this is 0. So equilibrium point, I'm putting a star on theta, means equilibrium point. This is convention. Sine theta star means that we are trying to do that. So this is equal to, from high school, sine of 0 is sine of k pi. When k is 0 plus minus 1 plus minus 2 and forever. So you see we have multiple equilibrium points, but we have to select a proper and a logical equilibrium point based on the real physics of the system. I'm going to explain why. So this is our pendulum. I'm plotting here. Until this point, everything is clear, guys? Yes? Yes, guys? Okay. Now, I'm selecting the first one. K is 0. If K is 0, this is going to be how much? It's going to be how much? 0. So your equilibrium point going to be 0. 0 angle. Means your hand is in the upright position. I'm sorry, in downward position. Here. Theta is 0. And this is logical. When you sit it there, just as like as you see here, put your hand in this position, parallel to your body. Does it move if you don't apply any torque on your shoulder? Does it move? If you don't apply any torque on the shoulder? No, it won't, right? Yes? See what I'm saying? So this is the equilibrium point of your system. Your hand doesn't move as you leave it free. See what I'm saying? Yes? Yes, everyone? What do you mean by ball? Yeah, well, see, here's theta, that's right. So here is theta 0, that's right. Here is theta 0, here is theta 0. So then theta is increasing. Like, so for example, here let's say theta is, for example, is pi over 4 or 45 degrees. See what I'm saying? So, so if you just do it, just put your hand as in this position, A, A prime. Just do it at home. So, does your hand move? Until you apply a torque or moment to your shoulder, right? So, so when it doesn't move, okay, and there is no force, this is definition of equilibrium point. See, system is at rest if you don't apply any external force, moment, or excitation. So this is your equilibrium point of your hand or the pendulum. So this is good. Okay, see what I'm saying? Okay, now let me try the other one. Say k is 1 because we are not done yet. So plus 1. If I do that, sine of theta star equals to sine of pi because k is 1. So your theta star gonna be pi. Pi means 180, right, sir? So means come here. This is 180 pi or 180 degree. Means that your pendulum I'm putting here. Guys, again, here is no friction. Friction means resisting, what the hell is that? Friction means resisting force, that's right. So if suppose that all of you raise your hand like this, and suppose that there is no friction, what's gonna happen? This is gonna remain here? This is gonna remain here? No. If you make all the zeros of your shoulder to 0, all the moments of your shoulder, it's gonna start rotates. That's right. Yes? See what I'm saying? Yes, everyone? Huh? Okay. So this is not equilibrium point. This is not equilibrium point, this position. Because without any force, it moves. So this is not a valid equilibrium point. This is not a valid equilibrium point. Because in this position, if you leave the system without any force, it remains there. But in this position, if you leave without any force, it's going to move. And this invalidates the definition of the equilibrium point. So our feasible equilibrium point is angle 0. So when you go to industry, when you drive differential equation, you may see different equilibrium points. You have to validate one by one based on the real physics of the system. See which of them works. See what I'm saying? The whole story? Yes? Good. So by theta star is 0. Now we found that. So what we're gonna do now, we have to linearize the sine of theta to a linear term. So we're gonna use Taylor series expansion. Taylor series expansion. Why? Because we derived the differential equation, it was nonlinear, we found the equilibrium point. Now we have to linearize the differential equation on the equilibrium point. Now we're gonna use Taylor series expansion. So, can I go to the next page? Yes? Okay. So, for a given nonlinear function, y is equal to fx, f is nonlinear, n is for nonlinear. So linear version of y gonna be based on equilibrium point of x star, means the equilibrium point now, you know that, is Fn at x star plus round Fn over round x at equilibrium point x star, x minus x star, here you have 1 factorial, plus round Fn second partial. Round means partial derivative, that's right, you know that from mathematics. Round xn square 2 factorial at where? At x is equal to x star, x minus x star square, plus continues round n. N means nth differential equation. N factorial round xn n at x is equal to x star, x minus x star to the power of n. This is Taylor series expansion. I bet almost all of you have seen this. So this is nonlinear function. For example, this is like this. Look like this: x cubed plus sine of x, say plus cosine of x. Okay. How we make it linearize? We find the equilibrium point as we did previously. Evaluate at this system. First time derivative, partial derivative, x minus x naught. So guys, but we don't need, you tell me, whatever is after here. Why we don't need those? We only need these. Why? I want that you tell me. We are linearizing nonlinear function. No. Guys, what is this from high school? It's a linear function or nonlinear function? Yeah. Y, x. Here we go. Right? Now what about this? Yeah. Because of what? This. So after this point, you're going to have x squared, x cubed, x4, xn. See what I'm saying? Yeah. So we don't need those. We only need x in the order of what? Order of 1. Clear, everyone? Yes? Okay. Having that, we're going to use this for your model of your hand. Or where is that? For this. Bingo. Oh. For this. And we're going to linearize distance, right? Because nonlinear term is this. Okay, let's go. We said the equilibrium point of the system we found together is 0, theta star. So what is our function? Our function is sine of theta. Exactly like this. So linear version of that is sine of theta at the equilibrium point. Sine of theta at the equilibrium point of the 0. Here we go. Plus first partial derivative with respect to x. Your x is here is what? Your variable is theta. So derivative of sine of theta with respect to theta. How much is that? From algebra. Yes. Cosine theta at where? At theta is the star is 0. See here? Here we go. So your variable theta minus theta star is 0. So this is equal to sine of 0 is 0, cosine of 0 is 1, and here is theta. So it is equal to theta. So you linearize it. So sine of theta at the equilibrium point of 0, you can approximate as theta, as a linear term, around the equilibrium point of the 0. Don't assume sine, cosine, tangent when they say your boss, you say that linearize it, it's going to be always theta or 1. I'm going to explain later. Because it depends on your equilibrium point. See what I'm saying? Maybe in some system, equilibrium point is pi over 4. You have to calculate this again. I'm talking about the equilibrium point of, you tell me, equilibrium point of 0. So, next page. Can I go to the next page? Sure. By convention means equilibrium point of theta. Right? I told here, see? See? Because we are trying to find the equilibrium point of theta, that's right. So if I say I want to find the equilibrium point of x, it's gonna be x star. I'm gonna find the equilibrium point of temperature, gonna be T star. I'm gonna find the equilibrium point of pressure, gonna be this. As I'm gonna teach you eventually, if I'm gonna find the equilibrium point of the flow rate, it's gonna be Q star. If I wanna find the equilibrium point of I don't know, equilibrium point of current, as I'm gonna teach you, is very heavy topic, gonna be I star. Okay, see what I'm saying? If I'm gonna find, as I'm gonna teach you, the valve rotation angle equilibrium point, gonna be alpha star. See? Clear, guys? Yep. Good. So where we were? So we found this, and now slide. So theta double dot, the model of your hand, G over L sine of theta is 0, because we found that. So we're gonna transfer it to theta double dot plus G over L theta, because we change it by linearizing, is 0. So now this is differential equation, linear differential equation. And eventually I can apply Laplace transform to this. I'm going to teach you this class and the control class, because undergraduate control and the modeling of physical systems is based on Laplace transform. Yep. Because we are trying to linearize, because we want to make a linear differential equation. This is nonlinear differential equation. What was your name? Yeah. And if I ask you, Joey, I give you 10 years, there's no analytical solution for this. But there is an analytical solution for this, as I'm going to do right now. Okay? And I'm going to discuss about the roots and the poles, because in the control and the modeling physical system, we're going to talk about poles and zeros of the system. See what I'm saying? Okay, so now we're going to solve this. In the vibration, I taught in ME430 that the name of this is what? Any of you remember? G over L for the pendulum? Omega n square. Natural frequency squared of the system. This is just a constant number, that's right? So it's gonna be theta double dot plus, all of you had vibration with me? All of you in last semester? Okay. Okay. I think that maybe 1/3 of the class they have. Okay. But if you don't worry, because I'm going to teach along with this why I'm naming this a natural frequency of the system. So now we have the linear differential equation. First, what I'm teaching this class, we are going to the MATLAB the next class, because I want that you know how to coding and these kind of things, okay? So the analytical solution from differential equation course is, this is homogeneous differential equation, because the right hand side is 0. That's right, is ESD. We're going to solve this by Laplace transform and the classical method that you know. So this is general solution. We name it general solution. General solution in differential equation. Why general? Because there is no force on the right hand side. Always in differential equation, always. For physical system, right hand side is a force. See, there is no force for the pendulum. External force. Or torque or moment, whatever. So theta dot, because we're gonna replace here, gonna be S ESD. Theta double dot gonna be S square ESD from high school. First time derivative, second time derivative. Everyone agree? Yes? So now I'm gonna use these two inside here. Here we go. Gonna be S square ESD plus omega n square ESD is 0. You can factor out ESD. S square plus omega n square is 0. Can this be 0, guys, this term? Can this term be 0? Can? Anyone? Yeah? Can it be 0? Just look at this. Can this be 0? Man, if this is 0, there is no solution. Your solution is 0. It's trivial solution. See what I'm saying? Yes? So this never can be 0. So what can be 0 is this. We are trying to find the solution of this differential equation. So S square gonna be minus omega n square. So you have two roots, S1 and 2 gonna be plus minus I omega n. Because why I? Because you have a negative here. You know that I is imaginary number, that's right, complex number. I is root square of minus 1. Everybody understand this? Yes? So you have we say a pair of imaginary roots. A pair of pure imaginary roots. So, can I go ahead? Yes? So, I'm gonna replace it here. So your theta of t gonna be a e I plus I omega nt plus b e minus I omega nt, because you have two roots, imaginary roots. Okay. So if I start eventually teach you the Laplace transform and the dynamical system in the frequency domain, as I'm going to teach eventually on the ME430, we're going in a complex number. It's going to be shown in this axis. Im means imaginary part of that and the real part of that. For example, sure. No problem, man. Okay. So if a is a complex number, oh, what happened? Oh, like as uh, a is a plus bi. So it's a part, real part. This is real part. Then gonna be a. Then the b is the imaginary part. So it's b. This is a. So this is your how we show. This is point A. This is point A here. So when your roots are pure imaginary, so you're gonna have, say here, plus I omega n minus I omega n. See, this is minus I omega n plus I omega n. This is how we show. So I'm going to discuss this. I'm not done because it's a very complex problem. So, okay, let's continue. So here I'm going to use Euler or Euler formula from undergraduate mathematics. Euler says E plus I omega, or say, let me change it to make it general. IA is cosine A plus minus I sine A, which is Euler formula. I bet we have seen this. So I'm going to apply to each of these. So the general solution, your hand, model of your hand, gonna be A cosine omega nt plus I sine omega nt plus B now cosine omega nt, because here is minus, takes minus I sine omega nt. So if you reorder based on sine and cosine, you're going to have A plus B cosine omega nt plus A minus B in I sine omega nt. So you can name it as C1, this is constant, and C2. So, when you're done, let me know. Can I go ahead? Okay. So your theta, angle of your hand, gonna be C1 cosine omega nt plus C2 sine omega nt. It's interesting, guys. It says your hand motion is based on sine and cosine. Means what? We're gonna see MATLAB eventually. Means if this is your hand, if you release from here, It's gonna oscillate like this. Ding, 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 ding. Sine and cosine, that's right. And that's why we name it natural frequency, because your system oscillates forever. Here we go. Here we go. We name it natural frequency because your system oscillates forever. Frequency means number of things happens per time unit. So frequency means that you have harmonic terms. Sine and cosine, they are harmonic terms. Because sine is like this, cosine is like this. So your hand gonna oscillate forever. If there is no friction in the shoulder joints and you release it from some non-zero angle, theta. From mathematics, you know that you can write it as this: d sine omega nt minus phi. You can write this final solution like this. Means your hand oscillates forever by sine. This is the amplitude of the vibration. Amplitude. And the phi is the phase angle. Phase angle. Do you know how to calculate d and phi based on C1 and C2? Yes? Do you know how to calculate d and phi based on C1 and C2? Yeah, okay. So do as homework for yourself. Okay? Derive d and phi based on C1 and C2 because this is very trivial. But the take-home message is that your hand gonna oscillate forever. That's why, so we modeled your hand. That's why you have a natural frequency. And the natural frequency of your hand, as we found from differential equation, is gravity divided by length of your hand. It's interesting, guys, because G, gravity in our planet, is constant on the surface of our planet. Is 9.81 meter per second squared. So, as you are a mechanical engineer and you have to only deal with mathematics, so natural frequency of your hand is almost a function of inverse of length of your hand because this is constant. Means if I increase the length of your hand, what happens for the natural frequency? If I increase the L, what happens for omega n? Decrease or increase? Yeah, decreases. What does it mean? It means if I have this, L is increased, you can also like this. Ling, 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 ling. Decreasing natural frequency means slower oscillation, right? I mean, you can test this in your grandpa or grandma old watches. If they have more lengths in the pendulum of the watch, they're gonna oscillate slowly. Now, if I decrease the length of that, what happens for the omega n? What happens for that? Omega n? Yes, means it's gonna oscillate fast. So I'm gonna show in the MATLAB, okay? Because this is modeling class. So if I decrease the length, it's gonna be ding, 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 ding. And this is math-based physics of mechanical engineering. Clear, guys? Good. So, okay, before leaving, can I go to the next page? Okay. I taught you when we were solving this, let me show you. The roots of this our general solution is a complex of a pure imaginary roots that later in this course and the automatic control course we're gonna name these poles of the system. Poles of the system. Poles, not roots. When we go to transfer function. Okay? So saying that, and I showed you that in the complex plane, a coordinate system, you had two pure plus omega n minus omega n, because here's imaginary part, I part. So now, by looking at these guys, and we know that regardless of the length of the pendulum, it's gonna oscillate forever. Is your system stable or unstable? Your system gonna oscillate forever. And the roots or the poles that I'm gonna teach you, they are pure imaginary roots or poles. Is your system, suppose that you graduated and you are working on the pendulum systems or whatever, and your boss asks this question, so can you regard your system as stable or unstable? Okay, now let me know what your system is, stable or unstable. What you told, I'm going to teach you the class later, not now, okay? But what your friend says, and he is right, if it's in the left, right of the imaginary axis, if your poles or the roots, your system is stable. If it's in the right side of the imaginary pole, your system is unstable. I'm going to teach you why later. But your poles or roots are exactly over the imaginary part. What your system is? It's on the border, that's right. On the border of stability and instability, right? Yes? Yes, guys? Exactly on the border. So that's why your hand is marginally stable. We name it, technical name in control, marginally stable. Any system that oscillates forever is marginally stable. Marginally stable. Any system that oscillates forever means its roots or its dominant roots or poles. I'm going to talk about these dominant poles. They are on the imaginary axis. So your system is marginally stable. It's going to oscillate forever. So if you have any system that their poles or roots, dominant one, is plus minus IA, means that your system is marginally stable. It's going to oscillate forever. So this is your function that you drive this and then design controller to make it stable. Okay? Clear, guys? Yes? Good. So we are done with the math. Hopefully we're gonna go to MATLAB the next class. Okay? Let me stop this.